Alright, so let's do part C. This one's actually a whole lot like part B. It just kind of has a little bit different twist on it, but you're going to use the loop rule to solve it much like part B. So if I say something you're not clear on, go back and watch part B. So C wants to calculate the energy stored in the 50 microfarad capacitor. Notice that says energy, not charge. Think about this. Capacitor, just think of capacitors kind of like this way if you're especially looking at energy and what kind it is, like if it's potential or kinetic. If it's not obvious to you, capacitors behave in systems a lot like, in electrical systems, a lot like springs behave in mechanical systems. They can store energy to like either be used later, or they can also kind of take in some of the energy, which could be used later or discharged somewhere else, just like a spring does. Think about like the kind that would, absorb extra energy, I guess, quote unquote, absorb extra energy, would be like the springs in your car suspension, or like mattress springs, or like, if there's springs in a sofa. And the ones that could store energy could be something like a slingshot, some springs on screen doors, a lot of different things like that. So just kind of, if you visualize them that way, it might be helpful to you. But anyway, that is to say that they are springs with the energy associated, capacitors. The energy associated with capacitors is potential energy, kind of like their spring potential energy. And some people, for some reason, did not believe me when I told them this. We have gone over it. On your equation sheet, you have potential energy, capacitors, potential energy, U sub C. There's two different forms of it, and both of them can be useful just depending on what variables you have. You've got the 1/2 Q delta V equals 1/2 C delta V squared, or you could just do like 1/2 QV or 1/2 CV squared. It actually, even the form looks a little bit like potential energy due to a spring for the one that has capacitance in it. So, just want to point that out. That being said, I've isolated loop 1 from up here. Just kind of drew it out to make it a little bit easier. This is your 30-volt battery. Again, if you put a voltmeter from here to here, if the circuit's in a steady state, this should read 30 volts. Now, in this particular case, though, get rid of that part right there. Remember, if you need to go back to part B, this is effectively gone because you have no current, because there's no place for it to travel. So that entire 30 volts is going to be your potential difference of the plates of the capacitor. So that is 30 volts. And technically, a lot of times your battery is negative and this would all equal 0, but I think I said this in an earlier video, we're just dealing with the numbers. So, equation-wise for your energy, it's going to be a potential energy in your capacitor. Well, you have your 1/2 CV squared, and you have all of this information. So, I'm going to go ahead and do the railroad track thing. Your capacitance is 5 microfarads, and your voltage is 30 volts. So I'm going to just do V squared over here as 30 squared, and that equals, I don't know if you can see this, 900 volts squared. So we would have up here 900 volts squared. So that's going to give you 5 times 900 is 4,500 microfarads volts squared over 2. 2 goes into 4 2 times. 2 goes into 5. Let's see, 2.5 times. So we'll get this. Think I'm right? No, it's not over anything. And by the way, microfarads times volts squared, well, what's your units for energy? Should be microjoules. Remember, mu is just 10 to the negative 6. So that would be how you'd find your energy.